Hi everyone. In lecture 9, we'll continue our discussion on bending loading and bending deformation. Before talking about new concept, as always, let's review the concepts we covered in previous lecture. So in previous lecture, first we discussed about how to solve the bending problem having relatively complex cross-sectional shape. And the step-by-step procedure are given as follows. First, we have to locate the centroid position, because when we write down the flexure formula or the expression for strain distribution, we use y equals 0 as the centroid position. If we don't know the centroid position, we cannot use this flexure formula at all. Okay, so for that, because if we have this rectangular cross section, it's really easy to locate the centroid. But when we have a little bit complex geometry and shape for cross sectional domain, we have to rely on the definition. However, what we have realized is that the definition of centroid is mathematically analogous to the definition of center of mass. And regarding the center of mass, we have intuition. Okay, the intuition we have is, if we can decompose the cross section into two parts, and if we can identify the centroid of each part relatively easily, we can use this expression. For example, the T-shaped cross-section that we discussed in previous section, we divided the section into upper section and bottom section, and the upper section can be approximated as rectangular, and lower section is also rectangle. So we can locate the centroid position really easily, y1 prime and y2 prime, and we multiply a1 and a2 for the centroid position of each, and divide that with A, because A is the total cross-section area, which is A1 plus A2. Okay, so if we use this mathematical intuition from freshman physics, we can locate centroid really easily. After locating the centroid, let's say the centroid here, we have to calculate I. Okay, but the definition of I is relatively complex, especially if we want to do this calculation as it is. It takes quite a long time. However, if you recall the rotation inertia chapter in freshman physics and the parallel axis theorem, if you know the centroid, if you know the I with respect to centroid, what you do is you add up the area multiplied by distance square, then you can obtain the contribution of the lower part in calculating I, and I with respect to the centroid of entire section. Okay, and you can do the same thing. This is the inertia for centroid of the upper rectangular block, and you add up area multiplied by distance to centroid of entire cross section. Then this is the application of parallel axis theorem, and you can obtain the I without performing the complex integral. After obtaining I and after obtaining y equals 0 position, then you can use flexure formula to obtain stress distribution, and out of stress distribution you can obtain maximum stress. If maximum stress is smaller than strength of the material, you can say that material is safe and reliable. This is regarding the safety design. And second thing is prediction of deformation. You can predict the bending radius of curvature using this formula. Okay, so this is the step-by-step procedure to handle a beam bending problem with relatively complex cross-sectional shape. And second kind of problem we considered was composite problem. So in composite problem, we considered this example. So upper body is composite of material 2, lower body is composite of material 1. And here, the one thing you have to remember is neutral plane is not centroid plane. Okay, so you gotta be careful about the definition of neutral plane and central plane. Centroid is the center of area, and the neutral plane is where the strain is 0. Okay, so for pure bending of homogeneous beam, yeah, you can say that neutral plane is centroid plane. However, for this composite cross section, yeah, you know such statement is not true anymore. So how do we approach the problem? So as you can see from this simple diagram and figure, what you can see here is, okay, the distribution of deformation and distribution of strain is the same as a simple homogeneous problem. Okay. However, when computing the stress, we have to multiply the modulus of each point, even though the strain is the same, because you don't have the same modulus at different position. Yeah, you're not gonna have a simple linear curve. You're gonna have this rather complex distribution of stress. Okay, so how do we approach the problem? Yeah, the way to approach this problem is we have to convert this problem into equivalent homogeneous problem. Okay, so yeah, first thing what you have to do is you have to convert this into equivalent homogeneous problem. So even though I only introduced to one choice, actually you can make a two choice. You can make a equivalent homogeneous problem with this lower material, or you can make a equivalent homogeneous material with upper material, so that yeah, you can have two choice. Okay, so here I define the ratio n as the modulus of material 1 and modulus of material 2. Okay, ratio of material 1 modulus ratio 2 material 2 modulus. Then second thing is, after converting this into homogeneous problem, yeah, your job is locate to centroid. And when obtaining centroid location, whether you have a first choice, whether you have second choice, the centroid position in y direction is of course independent of choice, because you only change the dimension in width direction. Okay, so the along the vertical direction you have same distribution of area, so centroid position is the same. Then after obtaining the centroid position, you can compute I. Of course, when computing I, you're gonna have different I, because I1 and I2, yeah, you have much larger mass in the second choice compared to first choice. Okay, so considering that the second choice have much larger width, yeah, you're gonna have much larger I for second choice in this case. Okay, then yeah, you gotta be really careful about this. Then as a first step, you have to apply flexure formula. Okay, when applying flexure formula, okay, I think I made a mistake here. Yeah, you have to when considering 1 over rho, yeah, you have to do this calculation m over e1 i1. You have to do you have to compute m over e2 i2. However, the different i1 and i2 effect is cancelled out here because you multiply different numbers. Okay, so when you focus on this, if you multiply e2 and considering that i2 is n i1, it's same as e1 i1, which becomes the same as the answer for first choice problem. Okay, so the reason I give you this example of making two choices is that I want to tell you that what kind of choice you make when considering equivalent homogeneous problem. In the end, yeah, you're gonna get the same answer, and you should get the same answer, right? So this is regarding the radius of curvature, yeah, for bending deformation. After obtaining this deformation, you can obtain the strain distribution really easily. So strain distribution, because we have the same law, yeah, it's independence of choice. And when you obtain the stress distribution, you have to multiply the Young's modulus for specific position. Of course, the distribution for stress should be independent of the choice. Okay, so whether you make a first choice or second choice, you in the end finally you're gonna get the same answer. Of course, in the way to the answer, you're gonna have different eyes, but it doesn't matter at all, because you're not gonna answer using this I1 and I2, because I1 and I2 does not have physical meaning, right? You just to make some mathematically equivalent problem. Other than that, final answer you're gonna half is like a bending radius of curvature, strain distribution, and stress distribution, and all of these final answers are independent of choice. Okay, so with that, I can finalize the review for the previous content, and we're gonna start discussion on new concepts in next video.